Welcome to the future of software management.
Yeah, it kind of feels like that sometimes, doesn't it?
Totally. Today, we're doing a deep dive into Docker. Really foundational stuff that kicked off a revolution back in, 2013?
That's right, 2013.
Yeah.
And we're going to focus on its three big innovations.
Yeah.
The Docker image, the Docker registry, and of course the Docker container.
Right, the big three.
And what's really cool, I think, is how they fit together. Docker always said like bread and butter.
Yeah, I remember that.
It forms that whole build, ship, run workflow.
Yeah.
And look, that's not just marketing speak. It's like a core assumption for basically everything in a cloud native computing foundation, the CNCF.
Absolutely. So yeah, our mission today for you listening is to kind of give you a shortcut. Help you really understand these three pieces and why they're still so important years later. Given how fundamental they are, what's maybe one thing you still see people getting maybe a bit wrong about how they connect, even now?
Well, that's a good one. I think a lot of folks still kind of see containers as just, lightweight VMs.
Right, like a smaller virtual machine.
Yeah. But the real genius, I think, is how they use existing OS features, Linux features mainly, to get that isolation without the whole separate OS. That makes them way lighter, way more portable.
Okay, so that's what we're going to unpack.
Exactly. Let's demystify it.
All right, let's do it. Kicking off with build. The Docker image. Now, it seems to me this was like the universal app packager people had been waiting for.
I'd say so, yeah. We had tons of package managers before, right? RPMs, debs, jars.
Oh, yeah.
But the Docker image was different. It's cross-OS, well, Linux and Windows primarily.
Right.
Cross-platform. And it doesn't care what language your app is written in.
Ah, okay.
Yeah.
So language agnostic.
Totally. It finally delivered on that write once, run anywhere idea, but, for the whole application stack.
Okay, so how do you actually make one? That's the Dockerfile. Yeah.
Exactly. The Dockerfile. Think of it like a recipe. Just a text file with instructions.
Step-by-step instructions.
Yep. And each command in there from RON, copy Y, those kinds of things, creates a distinct layer.
Layers. Why layers? What's the point?
Efficiency. Big time. They get moved around as these things called tarballs, basically compressed archives.
Yep.
They contain files, directories, permissions. The change is made by that specific command. So, say you start from a Python image.
Yeah.
That layer has the Python binaries, maybe libraries it needs, like OpenSSL.
Yeah.
But crucially, what it doesn't have are things like host machine drivers or the Linux kernel itself.
Ah, okay. So it only packs what the app needs.
Precisely. Keeps it lean,
Great.
just the application and its direct dependencies.
And then you just type Docker build.
You got it.
Yeah.
That one simple command takes that Docker file, all those instructions, processes the layers, and bam, you get a single optimized image. It's pretty slick engineering when you look under the hood.
Yeah, sounds like it.
And, that power and consistency, the image format itself, it just took off. It became so popular, it's now an actual industry standard, the OCI image standard.
Sure.
Open Container Initiative. Yeah, a whole group effort to keep container tech open and compatible.
Gotcha. Okay, so that's build. We've got our image. Now ship. That means the Docker registry.
Spot on. The registry is how you distribute these universal app packages we just talked about.
And I guess that's standardized now, too.
Yep. Also an OCI standard, often called the OCI distribution spec or registry specification. It just shows how widespread this whole approach has become.
And they really are everywhere, aren't they? I mean, every cloud provider, AWS, Google, Azure, they all have their own container registry.
Oh, absolutely. Plus Docker Hub, which is kind of the default and still hugely popular.
Right.
Then you've got GitHub packages, GitLab, Bitbucket, even self-hosted options like Harbor. Tons of choices.
So how do you know what you download is exactly what someone else built?
The SHA hash. Every image gets a unique cryptographic hash like a fingerprint based on its contents.
Okay, like a checksum?
Sort of, yeah. But cryptographically secure. It guarantees that when you Docker pull an image, you're getting an identical byte-for-byte copy of what was originally Docker pushed.
So Docker push uploads the layers to the registry.
And Docker pull downloads them to another machine.
Exactly. And that's the magic. You could build your app on, say, your laptop running Fedora,
Okay.
push it, then pull it onto a server running Ubuntu LTS in the cloud. And it runs identically. The underlying Linux distro differences, they just don't matter to the application inside the container.
Wow. That consistency must have been huge for teams.
Oh, it was a game changer. Absolutely massive.
Okay. Built the image, shipped it via registry. Now, the final step, run. the Docker container itself.
Right, so the image is downloaded onto a server, Linux or Windows. The Docker engine, the sort of runtime daemon,
Yeah.
that's what manages and orchestrates actually running it.
And the command for that is Docker run. Makes sense.
Yep, Docker run. That's the heart of the run phase. It takes the image and starts your application inside its own container. Okay, inside its own container. What does that actually mean? What is a container, really?
Good question. Fundamentally, it's about isolation. On Linux, it's mainly using features called namespaces.
Namespaces, okay.
Yeah. It gives the process inside the container its own view of the system, its own seemingly blank file system, populated from the image layers, of course,
Right.
its own IP address, its own virtual network interface, its own list of processes. From the app's point of view, it basically looks like it's running on its own dedicated machine.
But it's not. It's sharing the host kernel.
Exactly, sharing the host kernel, but isolated from the host and other containers. That isolation is super powerful.
How so?
Well, you can run multiple containers of the same Python app, for example, right next to each other.
Okay.
And they're completely separate. Change something in one, maybe install a different library version. The others are totally unaffected.
Ah, okay. That solves a lot of problems.
Definitely. And it's the foundation for scaling and high availability, too. You can just spin up many identical copies of your app container across different servers for redundancy or to handle more load.
So this whole build, ship, run workflow, it really underpins a lot of the modern stuff, doesn't it? Like Kubernetes, Helm.
Oh, absolutely essential. Yeah. Kubernetes basically assumes you have your apps packaged as container images ready to be pulled from a registry. It's the starting point for almost everything cloud native.
Right. So, okay, we understand the what, but maybe we should touch on the why. Why did Docker even need to exist? We had ways to package and deploy before.
Yeah, we did, but they had friction, lots of friction.
Yeah.
Docker really emerged to smooth out the whole software lifecycle, especially around packaging, distributing, and running apps. It basically tackled three big problems.
3 problems. Okay, let's break those down. What's the first one?
First pillar, let's call it isolation. This was about fixing the server problem. Remember back in the, say, 90s, early 2000s, servers were expensive. Big I. Yeah, so you'd cram multiple applications onto one machine to save costs.
Yeah.
But it was brittle.
Brittle how?
You'd have version conflicts all the time. This app needs Python 2.7. That one needs Python 3.6. This needs one version of Apache. That needs another. Managing it was a constant headache. Things broke easily.
Okay, yeah, I could see that. Then came VMs, virtual machines.
Right. VMs definitely provided isolation. You could give each app, or maybe a smaller group of apps, its own virtual server with its own OS.
Solved the conflict issue.
It did, but it created a new problem: OS sprawl. Suddenly, instead of managing one complex server, you were managing tens or hundreds of operating systems. Even with the cloud making VMs easy to spin up, the management overhead just shifted.
Right, patching all those OZs, configuring them.
Exactly. So Docker's solution here was genius. Containers give you that VM-like isolation, separate IP, file system process space, but crucially without needing a whole separate OS for each one.
Because they share the host OS kernel.
Precisely.
Yeah.
So you can run multiple apps, even different versions of the same app, on one host OS without them interfering. Fewer OASs to manage, fewer physical hosts needed. Big win for efficiency.
Okay, that's pillar 1, isolation. What's number 2?
Pillar 2 is environments. This tackles that classic, infamous problem. Well, it works on my machine.
The worst phrase in software development.
Isn't it just? It represented this matrix from hell where your app behaved differently on your Mac laptop versus the Windows test server versus the Linux production server.
Yeah, because the environments were subtly different. Different libraries, different paths, different configurations.
Exactly. Debugging was a nightmare. Deployments were terrifying because you never really knew if it would work the same way in production as it did in staging.
So how does Docker fix that?
Think about physical shipping containers.
Yeah.
The ones on ships and trains.
Yeah.
The beauty is the ship doesn't care what's inside the container. Could be bananas, could be electronics, and the stuff inside doesn't care what chip it's on. It's a standard box.
Ah, I see the analogy.
Docker does the same for software. The Docker image is that standard box. Thanks to the OCI standards we mentioned, it's a consistent format.
So the app runs with the exact same stuff it was built with.
Exactly the same. Dependencies, libraries, configuration files, everything it needs is packaged inside the image. So whether you run that container on your laptop or a test server, or in production cloud instances, it runs the same way. Consistency.
That is huge.
Right.
Okay, isolation, environments. What's the third pillar?
The third pillar is speed. And Let's be clear, we're not just talking CPU cycles here.
Okay.
We mean the speed of business. How fast can an organization take an idea for a piece of software and get it into the hands of customers?
Right. Time to market.
Exactly.
Yeah.
If you look at IT history, every major shift was driven by speed. Mainframes to PCs, distributed computing, faster access for individuals, bare metal servers to virtual machines, better hardware utilization, sure, but also faster deployment of server environments.
Yeah, spinning up a VM is way faster than racking a physical server.
Right. Then data centers to the cloud, near instant access to resources. Again, speed.
So where do containers fit in that progression?
They're the next logical step. VMs helped, but you still had OS sprawl. Containers let you pack workloads more densely onto fewer hosts by safely isolating them on the same kernel.
Less infrastructure overhead, faster scaling?
Precisely. Even things like serverless, AWS Lambda or Google Cloud Functions. Often behind the scenes, your code is actually running inside a container that spins up really fast.
Interesting. Didn't realize that.
So the overall impact is that Docker dramatically speeds up the whole life cycle. Developers can iterate faster locally, builds are faster and more consistent, testing is more reliable, and deployments much, much faster and safer.
So faster ideas to customer.
That's the bottom line. Speed of business.
Okay, that makes a lot of sense. The what and the why. Now, can we give people a taste of actually running one? Conceptually, at least?
Yeah, absolutely. And folks can actually try this super easily for free right in their web browser.
Oh, really? How?
There's a site called labs.play-with-docker.com. You just need a free Docker Hub account to log in, and it gives you a terminal in your browser connected to a machine with Docker ready to go. No install needed.
Oh, that's cool. Play with Docker. We should link that.
Definitely. And it helps illustrate that Docker usually works as a two-part system. You've got the command line client, the Docker command you type,
Right.
and that talks to the Docker engine, or daemon, which is the background service that actually does all the heavy lifting.
Client and server. Okay, so let's imagine we're in that Play with Docker terminal. What's a simple command?
Okay, a classic one is running a basic web server, like Apache. You could type docker run -dp 8800.80 HTTPD.
Okay, let's break that down. Docker run starts it. What's RED?
Docker run starts at HTTD.
.d means detached. Run the container in the background, basically. Don't tie up your terminal.
Got it. And HTTP 8800.80 looks like ports.
Yep, -p is for publish. It maps a port on the host machine, your Play with Docker machine in this case, port 8800 to a port inside the container, port 80.
Why port 80 inside? Because that's the default port the Apache web server, HTTPD is the image name for Apache, listens on for web traffic.
Ah, okay. So host port 8800 connects to container port 80.
You got it. And when you hit enter on that command,
Yeah.
a whole bunch of stuff happens pretty fast, mostly invisible to you.
Like what?
Well, Docker checks if you have the HTTPD image locally. If not, it pulls the layers from Docker Hub.
Right, the registry.
Then it creates the networking for the container, sets up that virtual network interface, create the container's file system from the image layer, sets up the port mapping you asked for, and finally starts the main Apache process inside the container.
Wow, okay. A lot going on.
Yeah, it's a neat orchestration. And then you could probably use a command like curl localhost 8800 right there in the terminal.
To see the Apache welcome page.
Exactly. To confirm it's running. And Docker Ops would show you your running container listed.
Cool. But here's the kicker, right? What if I run that same command again, but just change the host port? Like docker run -p 8801.80 HTTPD.
You'd get a second, completely separate Apache web server running.
On the same machine.
Yep. The first one is accessible on port 8800, the second on 8801. Inside each container, Apache is happily listening on its own port 80, totally unaware of the other one.
Because of the isolation.
Because of the isolation.
Yeah.
Docker manages the port mappings on the host so they don't collide. It really shows the power. And again, that magic is built on standard Linux features. Things like namespaces for that isolated view.
Right, you mentioned those.
Dot groups for limiting resources like CPU and memory for the container. Virtual Ethernet pairs called VETHs for networking. IP tables for the port mapping. Union mounts for layering the file system.
Okay. Lots of tech under the hood.
Yeah, but the point is it's not total magic.
Yeah.
A container is still running standard Linux processes on a standard, albeit usually much leaner, Linux file system. It's just cleverly walled off.
Makes sense. So, okay, as we kind of wrap this deep dive up, it really comes back to those three core things, doesn't it?
Absolutely. The Docker image, the Docker registry, and the Docker container. Build, ship, run. It's a powerful trifecta.
No. Yeah, a really elegant system for making software development and deployment more efficient.
And we saw why it was needed, right? It tackled those
Yeah.
big pain points. Better isolation than just piling apps on a server.
Without the overhead of VMs.
Right. Dramatically reduce the environmental differences.
Yeah.
That works on my machine problem.
Consistency across dev, test, prod.
And ultimately, it just massively increased the speed of business, getting software out faster.
So maybe a final thought for people listening. If this idea, this concept of self-contained portable units for complex systems worked so well for software, where else could that apply? You know, this principle of packaging complexity and ensuring it runs consistently regardless of the environment. Could we use that for managing other complex systems, maybe manufacturing, maybe even biological systems someday?
Ooh, that's a cool thought. Taking that core idea of containerization beyond just code.
Yeah.
How do you package and run complex multi-part systems reliably? Definitely something to chew on as tech keeps evolving.